Yeah, thanks for the nice introduction. And I also want to thank my co-authors, Simona Samardžička and Monika Trimoska. And yeah, it was really enjoyable to work with them. Yeah, this talk is about MQSign, which, so the name suggests it's a multivariate signature scheme. Okay. Okay, thank you. Yeah, it's a multivariate signature scheme, and it's based on UOV, and it's submitted to the KPQC competition, so the Korean standardization competition. So for a change, this is not about the NIST competition. I hope you will find that refreshing. There are 4 different variants of MQSign, and the last 2 letters suggest if part of the secret keys are chosen random or sparse. So first we have the MQSign RR, and this more or less corresponds to standard UOV. So there are some tweaks in the specification or implementation, but it's mostly the same. And then there are these sparse variants where part of the secret key is chosen sparse, so that we can reduce key size. So if you remember from yesterday, UOV suffers from these huge secret key sizes. So the idea was to choose sparse polynomials to reduce the key size. But yeah, today I will present attacks to every sparse variant. So first, I'm going to present a key recovery attack when the oil cross vinegar part is chosen sparse, which is very efficient. And yeah, and then I will show a forgery attack when the vinegar cross vinegar part is chosen sparse. But first, yeah, let's recall some properties of UOV and MQSign. Okay, so the main objects are the main objects in multivariate cryptography are quadratic maps. They map from FQN to FQM, so you can consider them as a collection of m polynomials in n variables. And the secret map or the central map, it's a quadratic map that is easy to invert. And yeah, this is achieved by this structure. So we divide the n variables into 2 sets, the vinegar and oil variables, and we allow quadratic vinegar terms, vinegar cross oil terms, but we do not allow quadratic oil terms. Yeah, as you heard yesterday, you can store the coefficients of these polynomials in a matrix or in matrices. And we see here this first part comes from the vinegar cross vinegar terms, the second part from the oil cross vinegar terms. And here, this 0 is really due to that we don't have any oil cross oil terms. And yesterday we saw symmetric matrices. So this was not 0 yesterday, but it is now. You can derive the symmetric part from this upper triangular one because the coefficients to the monomials, for example, for xi and xj are, yeah, they belong to the same monomial. So you can just store some. Just save some storage space if you just store the upper triangular part. Okay, and moreover, you also have this secret linear transformation, which is used to hide the structure of F. So together, F and S, they build the secret key. And commonly, we have that this secret transformation S is also of this special structure that we have the identity on the diagonal, and we really just have this this smaller submatrix which is the secret. Okay. Now to the public part of the UOV keys. These are public key maps that are maps that are hard to invert, quadratic maps that are hard to invert. So we see if we look more closely at the structure, there's not really any structure left. So they are seemingly random. And if we store the coefficients in a matrix, we don't get a 0 block here on the bottom right. We just get like a random looking upper triangular matrix. And the public and the secret key, they are related by this equation, but we have to be careful. This is not an equation of matrices. This is an equation of quadratic maps. So if we want to look at matrix equations, we have to consider these equations. And because, yeah, in this case, X is mapped to both sides of the matrix, we also have to apply this change of variables to both sides of F if we want to compute from F to P. So from the secret matrices to the public matrices. So we already see all we really need is the secret transformation S, and then we can compute the secret value from the public value. And yeah, how is this used to build a signature? First, we derive a target value from a message and a salt, and then we find a preimage under F, which is easy because they have the structure, and then we apply this matrix inversion to get the vector set, and set together with the salt gives us the signature. And if we want to verify, yeah, we just again build the target value and evaluate this vector set under the public key map and see if we really found a preimage. And yeah, if they coincide, then we accept the signature, otherwise we reject. And if we do not possess the secret key, so we don't know what F and S are, we had to invert this quadratic map P directly, and this is in general really hard. Okay, so far I've been only talking about UOV. Now what is special in MQSign is the usage of the sparse polynomials to reduce the key size. And yeah, we had these two blocks, first the vinegar block and then the vinegar cross oil block. And for the vinegar block, we do not allow, or the designers of MQSign, they do not allow coefficients for all monomials, but they yeah, fix this. They only allow V coefficients, and they take this index independence of the number of the polynomial as well. Yeah, we see in a second what that means for the structure of these matrices. But what is important here, by this, they can reduce the number of coefficients from around V squared over 2 to just V coefficients. And a similar thing is done for the oil cross vinegar part, where yeah, they reduce the coefficients from V times O, many coefficients here, to just V coefficients. Okay, so this reduces the key size a lot. But first, let's look at the matrix visualization of these polynomial equations. When we now store these polynomials into the matrices again, then we see, because if we look at the first polynomial, then we just have monomials of the form x1, x2, x2, x3, x3, x4. So they build a diagonal if we store them here. And if we go through the number of polynomials, for example, if we look at the second polynomial, this gets shifted to the right by 1. And this continues for all the polynomials. And yeah, the structure is chosen like this, I think, to avoid some rank defects and also to avoid some linearization attacks. For example, if we just would choose one row of coefficients and leave the rest 0, then we could just yeah, take out this complete polynomial equation by fixing one variable, because then we would linearize this equation by just fixing one variable, and this is not desired. So they use this approach instead. Okay, and we see by using these sparse polynomials, yeah, we can reduce the key size a lot. If we just choose one of these two block sparse, then it's reduced to around a half. And if we choose both of them sparse, we are left with around 5% of the initial key size. Okay, so much to UOV and MQSign. And now we come to the attacks. First, we start with a polynomial time key recovery. And what we use for this attack is, again, this matrix equation that I showed you earlier. And we already saw that there's a lot of structure in S and F. So if we look at this matrix equation in more detail, yeah, we just get this equation of submatrices. And important is the upper two blocks here, because the first block gives us that P1 equals F1. And the second block gives us this equation, and we can already substitute P1 into F1 because we see they're identical here, and we get this equation. And because we are interested in the secret matrix S, yeah, this is already interesting because this gives us linear equations in S. But the problem is, or the good thing is that they are highly underdetermined because we have a lot of secret coefficients in F2 here. So they somehow hide the values in S. Because for every equation we get from the entries of this matrix equation, we also get an unknown value in F2. Okay. But now in MQSign RS and MQSign SS, when F2 is chosen sparse, this is not the case anymore. So we see here, if we look at all the entries individually, we see here two public matrices and the secret one that we want to obtain. And here, this is also a secret matrix, but we know the structure of it because it is written in the specification. And yeah, for example, we look at the first entry and then we derive a linear equation, this time only in the variables of S, because here's no coefficient to hide or to obfuscate these equations. Okay, so we can continue and go through all the entries and collect a lot of linear equations. Because we also have many polynomials, so k is in the range from 1 to m, so we can, for every polynomial, we can collect more linear equations. And in total, we get way more equations than variables. And it's a linear system, so we can just solve it for the secret S. And once S is known, we can compute from the initial matrix equation, we can compute between the public and the secret polynomials as we wish. Okay, to summarize the attack, we compute the secret key really directly just from the values in the public key, so we don't need a signing oracle or anything. And since we just solve a lot of linear systems, it's a very efficient attack and it works in seconds for all security levels. And also closely after we published this result, Ikematsu et al., they managed to generalize the attack to arbitrary S. So we used S of this block structure as it is very common in UOV. But they generalized the attack to arbitrary S, and yeah, together this led to the removal of these two variants. So of the 4 variants, only these two are left. Okay, and now I want to show a forgery attack, which is a little more complicated and less efficient on the remaining sparse variant. Okay, so for a forgery attack, we have a target value T, which we derive from a message in the salt, so just from this digest here. And we directly try to find a preimage under P. So we would have to solve these M equations. K, again, ranges from 1 to M, so we have M equations, but these are quadratic equations, and they are hard to solve. But what we observe is that this part is sparse. So what we first do is that we eliminate the non-sparse submatrices from these quadratic equations by fixing set O randomly. And we can do that because we have more variables than equations, so we can spend some to get rid of this non-sparse submatrices. So what is left is still a quadratic system of M equations, but yeah, with only sparse quadratic monomials. And the key idea to our attack is now, or the key observation is that because of this special diagonal structure that I showed earlier, these M half of the equations, the one with an odd index K, if you look at these indices here, you can see that they are bilinear in the sets of set odd and set even. Because, for example, you have just monomials set 1, set 2, set 2, set 3, but you never get quadratic terms in the even variables, and you never get quadratic terms in the odd variables. So, yeah, in a nutshell, this is our attack strategy. We split the M equations into the M m/2 bilinear equations and the m/2 quadratic equations. And we also split the variables into the odd and the even ones. And the first step is now to guess the odd variables. So we have to guess v over 2 variables. And we can do that because we have only m/2 equations, and v is larger than m. And we get a v minus m/2 dimensional solution space for the even variables when we do that. For the m/2 bilinear equations, the problem is now that they will most likely not yield a solution to the m/2 quadratic equations that are not part of this bilinear set, because we had to guess too many variables. That means that we have to repeat the second step until we guessed correctly. So this is where the large complexity comes from this attack. And the second step is, after we fixed or we randomly guessed the odd variables, we solve for the even variables. And we have to find an assignment of set even for the remaining equations, the non-bilinear ones. And there we need to use this v minus m/2 dimensional linear solution space to get a solution in the remaining equations. And thereby we have to solve this quadratic system. But the number of variables is really limited. So this usually it takes a lot of time to solve a quadratic system, but because we have a limited number of variables, this can be done quite fast. So by there's the laser. Okay, so we have the enumeration step is really the costly step where we have to guess the variables and until we find correct ones. And the complexity of solving the quadratic system is, it's still quite large, but it's okay. So if we multiply these, or if we combine the complexity, we see that we are below the, a little bit below the security level that was targeted. And for the second step, we implemented the system solving step to validate these complexity estimates. And I think the complexity estimate for guessing the variables are clear, because it is just expected to that we need to guess this this number of times to find a correct solution. Okay. Now to the impact and maybe some open research questions. As I announced, I think the two variants here can be considered as broken due to our attack and also the generalization by Yukimatsu et al. And for the other sparse variable variant, I think for the MQSign advanced to the second competition round of the standardization process or this competition, and they tweaked this variant SR to LR. So I expect that our forgery attack does not work anymore because it made heavily use of this diagonal structure of the coefficient matrices. So it might be interesting to try and break MQSign LR or find some security flaws. Okay. So the takeaways which I want to give, maybe so sparse polynomials can introduce really vulnerabilities if you are not careful. For example, as our first attack has shown, if it allows you to derive many linear equations, then it can really be bad for the security of the scheme. But our attacks do not exploit a general weakness. So I think the usage of sparse polynomials is still interesting if you can reduce the key size by this. And for me, it seems preferable to choose public polynomials, the public polynomial sparse instead of the secret ones, as they can really give away some structure. Okay, that's it for my talk. Thanks for listening, and I'm happy to take your questions.
Are there questions?
Thank you for the talk. I wanted to ask for your forgery attack. Did you consider direct methods for trying to solve that system based on the fact that some of the equations are bilinear? Like, and I'm thinking along the lines of maybe an Excel approach where you're focusing on one variable set, or trying to balance out how you control degree with respect to each of the variable sets.
Yes. So what we did is um, I don't know if that is what you mean, but we like stopped at this step where we were only left with the sparse parts. So after we eliminated these non-sparse submatrices and tried to solve them directly with a system solving algorithm like Excel or F4, but it was not that efficient. If I remember correctly, it was just so we had this 2 to the power of 10 less. So you could subtract 10 or something from the exponent, but it wouldn't increase with a higher security level. So it was just more or less this. Yeah.
So your hybrid approach was just much more efficient.
Yes.
Yeah. Okay. Okay. Thank you.
Thanks.
For the talk. So in the same line than the question of Daniel, so I think you can probably derive the Hilbert series for your system, which is hybrid. This will give you the complexity of a direct approach of a Grosvenor basis or Excel technique on your system. And probably after you can do some hybrid approach on this bilinear structure. And probably you can control the complexity.
Okay, that sounds really interesting. Thank you.
I think we were a little bit behind, so I think that's all. And thanks, Thomas, again.